So this is the 3 discrete time sinusoids that we looked at before. This has a frequency omega naught over 2 pi that is equal to 1 over 12. Here we have omega naught over 2 pi that is 4 over 31. And here we have omega naught over 2 pi that is 2 pi over 6. Let's see. Oh, I'm sorry. Omega naught is 1 over 6, so this is 1 over 12 pi. Okay. So in this example, you see that omega naught over 2 pi is 1 over 12, which is rational. And therefore, you can always return back to the same point after n equal to 12 samples. Okay? So if you start from this point, right, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you return back to the same point. Okay? So a cycle, a period, okay, is n equal to 12. Right? So in this example here, we have omega naught over 2 pi that is 4 over 31. Okay. So 4 and 31 are co-prime. So you must sample at least 31 points in order to come back to the same value. Okay. So I don't know if we have enough points here, but all right, suppose you start from here. So suppose you start from here. Then you go 1, 2, 3, 4, 5, 6, 7, right? 7 or 8, both do not come back to this, right? But 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. We're a little bit short. 29, 30, 31, we should come back to this point. Okay? So, right. So we should come back to the same point, okay, after n equal to 31 samples. Okay? Now for this, omega naught over 2 pi is not rational. Okay? So it's impossible to come back to the same point over a finite number of samples. Okay? Right, so this is not periodic. Okay? So this is the key part of this lecture, right? To know the difference, okay, to know the difference between the periodic properties of continuous time and discrete time complex sinusoids. Okay? So if you compare, right, continuous time and a discrete time complex sinusoid, right, as mentioned before, right, in continuous time, you have a distinct signal for distinct values of omega naught. In fact, you have a signal that oscillates, faster and faster as omega naught increases for the continuous time case. But in the discrete time case, the behavior starts to repeat itself after multiples of 2 pi. Okay. Now, in the continuous time case, this signal is periodic for any choice of omega naught. But in the discrete time case, this is periodic only if omega naught is equal to 2 pi m over capital N, where both n and m are integers, meaning that m over n is rational. So this means that omega naught over 2 pi is rational. okay? And here, the fundamental frequency is omega naught, and the fundamental period, right, assuming omega naught is not equal to 0, is just 2 pi over omega naught, okay? Oh, I'm sorry. Yeah, the fundamental period is just 2 pi over omega naught, okay? Now, in the discrete time case, right, the fundamental frequency is omega naught over m, right? And the fundamental period, assuming it's the frequency is not 0, is m times 2 pi over omega naught. And this is when n and m are coprime.